Let's get started. Welcome back. I think before we begin, a couple of general topics and announcements. I think the third assignment is over now. So all the assignments are over. So you should get your third assignment back in a week. And Kaggle competition has started. I haven't seen the leaderboard if people have started making submissions. Okay, there are a couple of submissions. Okay, so there is one common request I received from students who are taking both my courses. So I think a lot of you who are taking, well, majority of the classes in Zoom today, but people here, like, how many of you are taking both ML and oral at the same time? Okay, there are a couple, but I would imagine there's a lot of people in the Zoom. Okay, so yeah, you can raise your hand. I can see hand raise count. So if you raise your hand, I can see the hand raise count. Okay, there are a lot of you in the Zoom. Okay, I understand that it is very difficult to do both the courses together, but my intention to keep them both in fall instead of keeping one in fall and another one in winter is because there is a lot of good follow-up courses for both the courses like that you can do in winter. Okay, so I would still like to keep both in fall. So I will see how to balance this load. If you find doing both the courses is overwhelming, like unfortunately this year everything is fixed. I cannot change the evaluation, but I mentioned in the oral lecture for people who are doing oral course, like, so I will try to, next year I'm definitely removing the project from the oral course so that like you have less load and you can focus on your assignments and Kaggle competition for machine learning and so on. Okay, so of course we cannot remove the Kaggle competition. So you will, I'm sure you will learn a lot in the competition as much as you have learned in the 3 assignments together. Okay, so it's a very practical assignment and it is very useful. Having said that, a lot of you worried that like with these 2 courses together and other courses to do, like I know that end of semester is always difficult. Like you'll have assignments, you'll have exams, you'll have Kaggle competition, projects, everything coming in. So, well, one thing that I can say, if that is going to help you relax a little bit, is I will be lenient on my gradings. Okay, so as I mentioned in the beginning of the course, these my courses are not for grades. Like these are graduate courses for undergraduates who are taking this course. Don't worry too much about grades. Like I will be lenient in the end. I know that you spent a lot of time in assignments and probably the Kaggle competition. So I will consider that. Like, so I will not be very harsh. Maybe you can ask people who took the ML course last semester. Like I was lenient and I will be lenient again. So don't stress too much. It is going to be difficult, especially towards the end of the semester. Like if you're doing 4 or 5 courses, but don't stress too much. Okay, so if you're stressed, you're not going to give you 100% for any of these courses. Like so only thing that I can do to help you is like I'll be more lenient. So don't worry too much about grades. Okay. Okay. So having said that, now let's get to the lecture. So last week we started discussing about neural networks, right? So the basic idea in neural networks is like, so far with all the other traditional machine learning algorithms that we have seen, like logistic regression or perceptron or SVM or decision trees, right? Like, so like we have to make sure that we have good representation so that these algorithms can do better, right? So in fact, in your third assignment, you did try 2 different types of representations to see which representation is better for text, right? Like, so now it was easy to do that for text, but for a lot of other practical problems, like engineering the features or representation of the input is a very hard problem. And the most attractive feature about neural network is the fact that you can actually learn these representations instead of just like relying on like someone hand engineering these representations, right? Like, so specifically, like if you take a 2-layer neural network architecture, it takes some input right? Let's say X. Okay. Now, in a perceptron, you would directly feed all these inputs to the perceptron unit, and it is going to make classification, right? So you will spend a lot of time here doing feature engineering, okay, where you take the X and you do some phi of X, okay, which is the basis function, and then you pass it to the neural network, right? Like, so now the idea for neural networks is the fact that you can actually remove all these difficult parts, okay, and automate that as well. Like, so instead of doing feature engineering, I'm going to take my input X, okay, and I'm going to just draw some random lines to say there are many lines. I'll compute H of X, okay, which is kind of my substitute for phi of X. Remember, phi of X was not learned, it was fixed, right? You do Gaussian basis function or you do like sigmoidal basis function, whatever, but it is fixed, right? On the other hand, in a neural network, we are going to have some parameter W, which constitutes our learned basis function H of X, okay? Now from this H of X, then I can pass it to the perceptron or SPM or whatever type of unit you want in the top, okay? Now this is going to have its own parameters. V, this is my output O, okay? Now this W is my projection parameter and V is my classification layer parameter, right? Like, so now we can learn all these things end to end by using gradient descent, okay? Now towards the end of the last lecture, like we discussed like how to do gradient descent, or specifically how to compute gradients when you have such sequence of functions put together, right? Like, so in this case, like you have the output, which is a function of hidden layer, which is a function of the input, right? Like, so when you have more layers, you can actually have many more such dependency in the sequence, right? Like, so whenever you have such chains, we can use the chain rule to compute the differentiation, right? Like, so now, especially with neural networks, like there is an efficient way to implement this chain rule, which is the idea of backpropagation. Okay. Now, what is backpropagation? So backpropagation is an efficient way of computing gradients in any layered model. Okay. So whenever you have layers, you can exploit the fact that there are layers by using dynamic programming and reduce your computations. Okay. So we started discussing about backpropagation in the last week. We are going to continue the discussion today. But to remind you, like what we have seen so far, like, so we took any neural network architecture, right? Like, so we added the laws also as units in the architecture. We computed this final scalar laws, and then we discussed a simple strategy to compute gradient backwards, right? Now, specifically, we looked at B diagrams. Okay, so there were 3 cases to consider, right? Like, so the first case was function composition. So when you have something like f of g of x, okay, and you want to compute gradient with respect to x, okay, now the way in which we will represent this in backpropagation diagram is like, so you take x, you first pass it through g, and then you pass it through f, right? So the right side of these units do the forward computation. Now the left side of these units will store the differentiation values. Okay. Now, when I do forward prop, okay, I'll start with x. I will do, so this is forward prop. Okay, in the forward prop, there will be x. After this unit, it becomes g of x, and after this unit, it becomes f of g of x. Right? Now, we also learned how to compute gradients by using backpropagation, which is basically the backprop, where I will start with the number 1, okay, and then I will multiply 1 with the left-hand side of the first unit. So this becomes f dash, right? So then I multiply this with the left hand side of the next unit. So this becomes f dash g dash. Okay, my output is f dash g dash. And we already know that dou by dou x of f of g of x is basically, first you differentiate f, then you differentiate g, right? So when I say f dash, it is basically dou f by dou x. Is that clear? Now this was a simple function decomposition. Now similarly, we also looked at function addition, right? So let's do addition quickly. So function addition, in this case, like I'm interested in computing the differentiation for f1 of x plus f2 of x. Let's say my y is equal to this. Now can somebody tell me what is my can somebody tell me what is dy by dx? Sorry? Yeah, so f1 dash, let's just call it as f1 dash, then plus f2 dash, right? So this is what we want. Now, how do we get this from the diagram? Like, so you have x. Now x is passed to two units in parallel. Like the first one is going to be f1, second one is going to be f2. And then you have an addition unit, which gives you f1 of x plus f2 of x, right? So the forward prop is clear. Now let's do back prop. So when we do back prop, I'll put number 1 here. Okay. Well, we need the differentials, right? So f1 dash, f2 dash, and we know that whenever we sum, the difference is 1. Like the gradient is 1. Okay. So now I put a 1 here. So there is a splitting happening here. So this 1 is going to go this path as well as this path. Okay, whenever it combines, we will add the gradients. Okay, so 1 multiplied by 1 is 1. 1 multiplied by 1 is 1. Right? Now it goes further. So multiplied by f1 dash, it becomes f1 dash. Multiplied by f2 dash, it becomes f2 dash. Okay, and whenever you have this thing merging, you combine, so you get f1 dash plus f2 dash. Is that clear? Now this is the second case, and the third case that we saw was the simple weighted edge, right? So the idea is like you have some input x, it passes through some weighted edge. Like this is how the neural network architecture is, right? Like so you have a W connecting like one unit in one layer to another unit in another layer. So the output is WX. So the backprop here is really simple. Like all you have to do is put a 1. Whenever there is a weight, you multiply by the weight. So 1 into W, W. So the output is W. And we already know that dou by dou x of WX is basically W. Right? Now, just putting these 3 simple basic blocks together, we can compute gradient for any architecture. Okay, so all we have to do is first represent the architecture in B diagram, where in every unit you compute the forward prop and also the backward prop. Okay, and once you take a forward pass, you are in the end, you put a 1 and you go back. When you go back, you are going to follow these 3 rules, like rule for composition, rule for addition, and rule for weights, right? So you follow these rules and reach the input. So let's say this is my architecture, which takes x as input and makes some output, let's say O, or let us just directly call the loss. Okay. Now, when I do backprop and reach my input again, I would get dou loss by dou x. Is that clear? So any question about the algorithm? Any question in chat? Okay. So what was our goal? Was our goal to compute gradient with respect to the input? What do we care about in learning?
Gradient descent.
Yeah, so what do you need for gradient descent?
Error function.
Okay, so what is the update equation for my gradient descent, right? Like, let's say my parameter is W. Then the gradient descent update equation is going to be W is equal to W minus alpha times dou loss by dou W. Is that right? So I have to compute gradient with respect to the parameters. However, the algorithm that I have explained you so far is computing the gradient with respect to the input. Right? Now, we need to slightly change this algorithm. It's not a big change. Like with a very little change, like we can get dou loss by dou W from dou loss by dou X. Okay? So we will do that shortly. But before we do that, we are first going to prove that this algorithm that I described, right? Like, so will indeed compute the correct gradient for any arbitrary network structure. Okay, so we don't do a lot of proofs in this course. Like, so it's this is not really a big proof. Like, it's like I'm just going to give you a very hand wavy argument, but the detailed proof is in the lecture notes. Okay, so the proposition I want to prove is the backprop algorithm computes the derivative of the network function f, okay, with respect to the input x correctly. Okay, because I showed you these simple 3 examples where it so happens that the output is correct. What if I give you a really complex architecture, like a lot of units and lots of connections and lots of additions and so on, right? Like, so can this algorithm still give me exact answer? Okay, or there's going to be error. So we're going to prove that this is indeed going to give us the correct gradient, but by using the idea of proof by induction. So how many of you have seen proof by induction before? Hand raise. You can use hand raise in the Zoom. People in Zoom, use your hand raise feature. Okay, so can I see the hand raise in class again? Okay. Okay, I was expecting almost all of you to know proof by induction if you're from computer science or computer engineering. Okay, so I know that this class is very diverse. Like, there are a lot of students from outside informatics. So for people who already know proof by induction, like, it might be easy to follow. For others, here's the general 30-second introduction to proof by induction. So what I'm going to do is I'm going to prove a set of base cases. Okay, now we have already done that. The 3 cases that we have seen are actually the base cases. Okay, so the base cases are what happens if my units are in series, sequence or function composition. Okay, and the second base case is units in parallel. This is the addition thing that we have seen. And the third base case is weighted edges. Okay, so we covered them in detail. Like, we have already proved these base cases. Okay, now the way in which proof by induction would work is we'll prove a bunch of base cases. When we're using the base cases, okay, and an inductive hypothesis that the algorithm works for, let's say, up to n nodes, I'm going to prove that it will work for n plus 1 nodes. Is that clear? So the hypothesis that I have, induction hypothesis, is the algorithm works for any feed-forward network, okay, with n or fewer nodes. Okay, I'm going to assume that the algorithm works for n nodes, and I'm going to prove that if the algorithm works for n nodes, okay, it will also work for n plus 1 network. Is that clear? Any question? Now you understand the logic, right? Like, so once I prove that if it works for n nodes and it works for n plus one node, then the general thing holds. Like, so it will work for, we already know that it works for one or two nodes based on the base case. From the base case, I can develop that, okay, then it will work for 3 nodes, then it will work for 4 nodes, and so on. And in general, it is going to work for any number of nodes. Okay. Now, I'm just going to do a proof by picture. Okay, so it's simpler than writing arguments. So here is like a network architecture. You take X as input. Okay. We don't care how many layers are there, how many units are there. Okay. Let us just assume that there is one layer in the n, which is computing f1 of x, f2 of x to fm of x. Okay. So then there is a final unit which has weights w1, w2, w3, and it is doing some phi of s. Okay. So it could be any activation function, sigmoid or tan h, and you also have phi dash of s here, and the final output is f of s. Okay. Now this is my architecture. Now what will be the equation for this architecture? The equation is f of x, which is basically phi of the incoming input, right? So phi of w1 f1 of x plus w2 f2 of x plus wm fm of x. Is that clear? Okay. Now forget about back propagation. Let us just do this differentiation by hand, by ourselves. Okay. Now what would be the f? What would be f dash of x here? Anybody? I want to differentiate this function with respect to fx. Yeah.
It would be phi dash of the rest of what's
Phi dash of, let's just say the whole thing is yes. Okay.
Yeah. Multiplied by the sum of w1 weight 1 times f1 dash.
Okay. So then you do the differentiation inside. So it becomes w1 times f1 dash of x plus w2 times f2 dash of x plus wm times fm dash of x. Is that right? Now this is what we want, right? So here is my argument. Let's go back here. I told you that this whole neural network architecture has n plus 1 nodes. Okay. Now think about starting from x and all the computation up to f1 of x. Okay. Now, what can you say about the number of nodes in this subnetwork? Any guess? Yeah.
It's smaller than the overall.
Smaller than?
The.
It is definitely less than n plus 1, right? So we know that at least it is less than n, like there is one output unit and there are m minus 1 other units. So it is like m times lesser than like n plus 1. It's n plus 1 minus m specifically, exactly, right? So now our assumption is up to n nodes, my algorithm will compute f dash of x perfectly. Okay. According to my assumption, I can take this subnetwork and run back propagation. It is going to give me f1 dash of x, right? Is that right? Similarly, I can take this subnetwork, the blue subnetwork, which ends at f2 dash of x. Okay, that is f2 of x. Okay, like if I do a backprop for this, I will get f2 dash of x, and so on. Right? Now, let me put a 1 here. Okay, and do backprop. So 1 will be multiplied by phi dash of yes. So I'll get phi dash of yes. Okay. Then this phi dash of x is parallelly broadcasted to all the weights, right? So when it crosses this, it becomes phi dash of yes, okay, multiplied by W1. So when it passes through this, it becomes phi dash of yes multiplied by W2, phi dash of yes multiplied by Wm, right? So then it goes to this unit. For this unit, we know that we can compute f1 dash of x already. That is what going to be there in the left side, right? So you multiply by that. Okay. So do you see what happens? Like, so when I run this backprop, I actually get, so the whole thing comes here and it will get added. So there will be phi dash of yes, W1 times f1 dash of x, okay, plus phi dash of yes, W2 times f2 dash of x, plus phi dash of yes, Wm times fm dash of x, right? So I can just take the phi dash of s outside. So phi dash of s times W1 f1 dash of x plus, sorry, W2 f2 dash of x plus Wm fm dash of x. Okay, I think we have to wait for the screen to clear. Okay, let's just give it a 10-second. What happened to the screen? Okay. Is that clear? So what I have proved is if backprop works for n nodes, it will work for n plus 1 nodes. Now I can just generalize this. Okay, so this is in fact this algorithmic idea, like which you can actually implement, is in fact giving us correct gradients with respect to input. Okay, now so far I only talked about one input unit, right? Like, so just x, but you can have any number of input units. Like, so for example, if you have two x1 and x2, okay, and you have a function f, okay, now you can store two gradients here, like one for dou f by dou x1 and another for dou f by dou x2. Is that clear? So to get dou f by dou x1, all you have to do is put a 1 and follow the track all the way to x1. For x2, you follow the path all the way to x2. Is that clear? Any questions? Now we can talk about how to use this for gradient descent, but any question before that? Maybe in chat. Okay, so now let's talk about how to do learning with backprop. Okay, now let us consider any weight Wij. Okay, Wij is a weight connecting ith unit in previous layer to the jth unit in the next layer. Is that clear? So let's say this is my node I, this is my node j, and this is Wij. Okay. Now, there is a big network here, and there's also a network here. And this network ends in final loss, right? And this network ends in X. Okay. Now, we are interested in computing dou loss by dou Wij, right? That is what we want. Now, there is a very easy way to change the backprop algorithm that we saw now. Like, so imagine the output of this unit, let's just call it OI. Okay. Now, imagine this particular, let me change my shade. Imagine this particular network, which is starting at jth unit, right, and ending in the error. You can treat this as one specific network, which has input x equal to OI times Wij. Is that clear? For this particular blue network, okay, the input x is given by OI multiplied by Wij. Okay, now I can just run the backprop as usual. I'm going to get dou E by dou Wij. Okay, let's just call this the error E. Okay, so dou E by dou Wij is nothing but dou E by dou x by dou Wij. Okay, now we know how to compute dou E by dou x. Okay, so and dou x by dou Wij is nothing but OI, right? So OI multiplied by the first term, I'm putting it as the second term here, dou E by dou OI Wij. Is that clear? Now you can actually compute gradient with respect to the parameters. Now, one thing you should notice is like to compute gradient with respect to the parameters, you actually have to store OIs. Like you also have to store the right-hand side of the units. Now, for every unit, you should store both the right-hand side and the left-hand side. Is that clear? Now, the cumulative. Okay, so at each unit, okay, I'm going to store the output OI, okay, and I'm also going to store the cumulative backprop result. Starting from number 1, you multiply all the gradients like until this particular part of the chain, right? Like so, you have this backpropagated error. Okay, so we're going to call that backpropagated error as delta. Okay, so dou E by dou Wij is equal to OI multiplied by del J. Del J is the backpropagated error that you're getting to this node. Is that clear? So then I can update my Wij by using gradient descent. So Wij is equal to Wij minus alpha times dou E by dou Wij. Is that clear? Any question? Yeah.
Wasn't the derivative of the first slide dou E over dou OI Wij? Why is it only over Wij?
Oh, because we converted it, right? Like so, you can actually convert. So this whole thing, dou E by dou OI Wij, we are going to call this as del J. Okay, so then you have this thing. Okay. Okay, so now we have seen the most general case of backpropagation. Okay, it could work for any arbitrary architecture like that you can think of. But for most of our practical purposes, like we will be using a fully connected feed-forward neural network, like so where you have like which will look something like this. Okay, so you will have a bunch of units, input units. Let's just call them as input units. Okay. Now let's say I have n input units. Okay. Then I would have a bunch of hidden units. Okay. Let us just say there are k hidden units. Okay. And let us say there are m output units. Okay. In a fully connected architecture, each unit is going to be connected with all the units from the next layer. Is that clear? Okay. Okay. Now, how would you represent the first part? So the first part is represented as, let's say, sigma of W1x plus B1. Okay, just as an example. The second part will be represented as sigma of W2H plus B2. Okay, now to make the equations easier for us, we are going to put the bias inside the W. Okay, so how would you do that? So the easy way to do that is by adding a unit called 1. Okay, to avoid the confusion, let's just put a 1 here. You can add a unit 1 here and connect this unit to all the layers. Now that is my bias. Is that clear? So instead of using W1, so W1 here was a n cross k matrix, right? It goes from n to k units. Similarly, W2 was a k cross m matrix. Now I can just put the bias inside, so I can have W1 bar, which is n plus 1 cross k matrix. Okay. Similarly, W2 bar, which is k plus 1 times m matrix. Is that clear? Okay. Now, when you have a fully connected architecture like this, the backprop equations are going to be much more simple and compact. Okay, so you're going to do that now. It's easy. It's going to be simpler in the sense you can just write the whole update step with just matrix vector operations. Okay, so let us see how to do that. So now there are 2 layers here, right? So we're just going to call the first layer as any weight in the first layer as Wij of 1. Any weight in the second layer as Wij of 2. Just to give us some names. Okay. Now, the input of the neural network is n dimensional, right? So let us just take some input. Okay, I'm going to call the input as O, like output, because we are going to use it for all the layers. So O is going to be O1 to On. Okay. Now I can add an extra 1 to this input so that bias is considered. So I have O hat, which is O1 to On with an extra 1. Is that clear? Now, in any layer, you're going to have a pre-activation, which is, let's just say, net j is equal to summation over I is equal to 1 to n plus 1, Wij of 1 times Y. Is that clear? I take the input, I pass it through the first layer, I get my jth unit in the intermediate representation. Okay, then I can compute Oj of 1, which is the output of the first layer, as nothing but some function s of summation n is equal to 1 to n plus 1, Wij of 1 y. Is that clear? Okay. Now, this can be written efficiently by using matrix operations. Okay, so here is my hidden layer equation. My hidden layer O of 1 can be written as S of OW1 bar. Okay, now, so here you see that you take the input O hat, okay, and it's a vector, right? So you take this vector, you multiply with the matrix W1 bar, okay, you're going to get another vector. For that vector, you apply your activation function. It could be sigmoid or tan h, any function. Okay. So then you get O1. O1 is actually our h of x. Okay. Now you take this O1 as input and pass it to the next layer. So that will give you the O2. O2 is my final output. My final output is given by some function of O1 1 times W2 bar. Is that clear? Now I can actually generalize this to any number of layers. Like, so I can do O3, which is S of O22 of W2 bar, so W3 bar, and so on, right? Like, so you can extend this to as many layers as you want. Is that clear? Okay. Now let's compute the gradient for this specific model that we have here. We have both hidden layer and the output. Okay. Now this is my algorithm. Like, this is my model, and we are going to compute gradients with respect to the weights W1 and W2. Okay. Now, if we have to do it manually, it's really simple, right? Like, so all you have to do is like backprop. Like, all you have to do is like compute the chain rule. Like, so you'll differentiate with respect to S, and then you will differentiate with respect to S, and then with respect to this, and then you go here, and then with respect to this, and then with respect to this, right? Like, so you can do the chain rule by yourself. But instead, we are going to see how to do backprop for this particular model. Okay. Now, here are the steps of the algorithm. So, as usual, we are going to do an extended network. Okay. So which means I'm going to take the loss, and I'm also going to put the loss inside my network. Okay. Let us consider squared error, for example. We are interested in doing squared error for my given output. Okay. Now, this is my ith hidden unit. Okay. And the output of this unit is going to be OI of 1. Okay. Now, there are a bunch of output units. Yes, dash, dash. Okay, they all get the incoming weights, right? So we are going to consider only WIM, some WIJ of 2. Okay, this is WIM of 2. Now, if you have this weight, it is going to be WI1 of 2, right? Now, all these output units give you some output. So O1 of 2, O2 of 2, OM of 2. Right? Now I'm going to add new nodes. Like, I'm going to add one node for every loss in the unit. Like, so for the first unit, the loss is given by 1 over 2, O1 of 2 minus T1 the whole square. Okay. Similarly, the second one is given by 1 over 2, O2 of 2 minus T2 the whole square. And finally, 1 over 2, OM of 2 minus T1, TM the whole square. Then you add all these things with a plus symbol, and then you get the error. Is that clear? Now we also need to compute the differentiation, right? Like the differentiation of 1 over 2 O minus T the whole square. It's x squared. Differentiate, you get 2x, 2 cancels each. Like, you just have O1 of 2 minus T1. Similarly, O2 of 2 minus T2, OM of 2 minus TM. Is that clear? Okay. As a first step, we will compute gradient for the hidden to output layer. Then we will compute the gradient for input to hidden layer. Okay, then we are done. Now, how do we compute gradient for output, like input to hidden to output layer, right? So now, in case of forward propagation, it is easy. You will start with the input. You will send the input to the first hidden layer. Then you will send the input to the output layer. Then you send the input to the last layer. You get the loss, right? Now we're going to do backprop. Okay, so we're going to do backprop. Okay. And our first goal is to compute dou E by dou Wij of. Is that clear? Now, how do we do that? So this is really simple. Like, so now you can see, let's just take the diagram again. So this is my ith hidden unit, which has OI of 1 as in output. Okay, this is my ith hidden unit. Okay, now from here I get Wij of 2, which is what I care about, and this takes me to the jth output unit, so Oj of 2. Okay, so let us assume that we are using a sigmoid activation. Then what would be the differentiation of this Oj? Sorry? So what is differentiation of sigmoid? Sigma into 1 minus sigma, right? So it's going to be Oj into 1 minus Oj. Okay, so then it goes to the mean square error, like, so it's 1 over 2 Oj of 2 minus Tj the whole square, Oj of 2 minus Tj, and all of them gets added by the plus, and then you get the error, right? So now I can actually do back propagation through this. Let's see what happens. I'll put a 1 here, okay, and that 1 goes through this, so it is still 1, and that 1 goes through this, so you get Oj of 2 minus Tj. Okay, it goes through this, so now you're going to multiply this with whatever is there, right? Like, so it becomes Oj of 2 1 minus Oj of 2 multiplied by Oj of 2 minus Tj, right? Now this is the gradient. This is the one for which we are looking for gradient, right? So now we have already computed that dou E by dou Wij of 2 is going to be OI1, the input, multiplied by the del J of 2, right? The del J of 2 is basically whatever value you have accumulated so far. So which is what is given by this particular value. So my del J of 2 is nothing but Oj of 2 times 1 minus Oj of 2, and then Oj of 2 minus Tj. Is that clear? So I have computed the gradient with respect to my hidden to output weights. Okay. Now I just need to compute my gradient with respect to hidden to input or input to hidden weights. Then we are done. Okay. So we will take a small break here. So we will continue in 10 minutes. There is actually a question in the chat, but I will take that after the break.